So if I revise, if I go back, right, the solution of a D latch to a D flip-flop was this, right? We had this is a latch which is level triggered. This is another latch, I call it latch 1. This is another latch, latch 2, which is again level triggered, right? But as you can see, this is connected with clock bar and this is connected with clock, right? So this gives rise to an edge triggering effect, because as you can see, the first latch is going to be triggered. Let's say this is your clock, and I'll draw with a different color. So this is your, let's say, clock, and the clock bar is going to look like this, right? This is your clock bar. So as you can see, the only time, a very small fraction of time that is going to allow the output of latch 1 to be copied to the output of latch 2 or Q is when both of them are 1, because both of them needs to be level triggered. Okay, so the only time that will happen is in the junction when the first clock goes from 0 to high, right? 0 to high. So because this is the time when the first flip-flop or the flip-flop, or sorry, the latch that has a clock as an input, which is L2, is going to allow this output to be written to this output. Whereas it is completely the opposite in case of the first latch. Okay, so these green parts are the times when the output of the first latch could be going to the output of the second latch. Okay, so these are the green times, and if I mark with a different color the times where output of the input of the first latch is copied to the output of the first latch, is basically these parts, right? So if you can think that when is this output, this input to this latch is going to be copied here, and this is also going to be copied to output, is only this period of time. So a very small period of time, right, where there is a positive edge trigger. Okay, so this positive edge trigger was found out by using this mechanism of having a inverted clock to one of the latches, right? So even you can, if you do not want to use this negation here, you can directly give the clock and you can give a clock bar here in that case, right? So that will always create a complementary relationship with the timings when the input to a latch is copied to the output of the latch. Okay, so this is the same mechanism we are going to use for creating the JK flip-flop also. Okay, so this was a conversion from a D latch to a D flip-flop, where we join together these two D latches consecutively, but with a different or a negated clock input. So that negated clock input is the key to create this edge triggering from level triggering. And how it is done, I have kind of shown you an intuition. You can work it out. So whenever this is high, the other one is low. Whenever this is the other one is low, the other one is high, right? So vice versa relationship. In the junction, there is a trigger, because this is high, this is low, this is low, this is high. But whenever there is a transition, there is a very small period of time when both of them will be kind of in the high state, and this is going to result in an edge, right? So there will be an edge which is produced here. There will be an edge which is produced here. So we are only talking about positive edges. Okay, so you have to see why we are not looking at negative edges. In this case, we are just considering the positive edges. That is, the main clock goes from low to high. Okay, if you are trying to work with a negative edge triggered circuit, then in that case we are going to use clocks going from high to low. Okay, for our condition, for our most of our discussion, we are going to use from low to high. Okay, this is called a positive edge trigger. Similarly, in case of J flip-flop, JK flip-flop also, we are going to have a very similar story where we are going to show you the architecture to avoid this race condition. And this architecture is something like this, right? Do not look at the picture as a whole, right? What we can show you first is that look at or appreciate the fact that this actually consists of two JK flip-flops, right? Sometimes we call it a JK flip-flop or a JK latch actually because it behaves as a latch, right? So there is a confusion in the terminology sometimes. This is for some reason called a master-slave JK flip-flop that consists of these two JK latches. One is the master latch, the other one is the slave latch. So exactly this part is a circuit which is equivalent to the same thing we did it with case of D latch also, and this is the first one, right, where the input directly comes. Okay, so this is the second one. UPS is there. Okay, and this is the first one. Okay, but note that this clock input is not the same as this clock input, right? Because the clock is actually negated here. So there is an inverter here, and this inverter is going to convert the clock into clock bar. This is again the crux through which the edge triggering is taking place. So as you can see, the race condition is of course going to be here. So this output is going to show this racing phenomenon. Okay, racing will happen here, but this is going to latch at the edge trigger, right? So this is racing, although it may happen here, we will not get a race condition at the final output Q. So here no racing, okay, because individually although they are level triggered, right? Because the first one, as you can see, this is a level triggering. Here also we are having a level triggering. Okay, this is with a clock and this is with a clock bar. Okay, so effectively what we are getting is you start avoiding that metastable condition in the final output Q. You are not going to have any race condition, and you can verify yourself that once this has passed, it is going to be locked. Okay, the output is not going to toggle for this infinite amount of time. Okay, so this feedback, as you are seeing now, goes back. This feedback also goes back. Okay, but this is not going to be an issue because only in the next clock trigger, from low to high trigger only, the toggling will take place. Okay, before that the toggling will not take place because there is no feedback from the first latch to the inputs, right? Only from the second latch or the slave latch there is a feedback. This feedback is there. Okay, feedback from slave output to JK inputs. Okay, and here we are having no feedbacks. Okay, so this phenomenon, although it would have been possible if you had a feedback, will not happen anyway. Okay, because that feed only if there is a feedback from the output to the original input, that thing is going to happen. In that case, this is not happening. So that's why the values that you are going to copy here is going to be permanently latched before the level changes. Okay, or the next trigger happens. That is how the circuit is architected. Okay, so this is going to be often called a master slave JK flip-flop, or sometimes people commonly refer to as a JK flip-flop. It is understood that it's a master slave JK flip-flop and race condition does not arise here. Sometimes explicitly they will not call this a master slave JK flip-flop, simply JK flip-flop they will say. Okay, so if you come across a JK flip-flop in a book, this is often a master slave JK flip-flop, right? Because the other one is mostly or more like a latch. Okay, this is a level trigger device. Okay, there is some confusion in the terminology and the jargons often, but always remember, if you are using the word flip-flop, this actually denotes a device that is activated on the trigger of the clock or the state change of the clock. It has to be either low to high or high to low or both, but the state change is very important. In case of a latch, it is always whether the clock is low or high. This is called active low or high, right? Or active high, right? Which is basically high, same thing. But remember that the amount of time the clock is going to be high is the same as the amount of time the flip-flop is also going to be on, which is not the case in case of a edge triggered circuit, which is a flip-flop. So we looked at both the kind of flip-flops. One is the D-Flipflop, the other one is a JK flip-flop. Okay, so this is the final master slave configuration. Note that there is no feedback here. Also, there is no feedback. Okay, and this is your feedback. Same here. So in effect, you are getting the toggle and locking it, right? You are getting the first toggle, you are locking it, whatever be the time it takes from going from 0 to 1 for the clock. Maybe it is some finite amount of time, but there is no scope of infinite toggles, right? Because I am only concentrating on the edge, okay, edge of the triggering pulse. Okay, so it doesn't matter whether your clock looks like this or the clock is very, very narrow or the clock is very, very wide, right? So this is your clock input. So in our common sense, if we are using the JK in the latch configuration, the wider pulse are not favored because this amount of time, let's say this amount of time or this amount of time, this is going to lead to uncontrolled toggling, okay, for a JK latch configuration. Whereas it doesn't matter in case of a master slave JK flip-flop, doesn't matter what kind of clock input you are giving, because all of these circuits, or sorry, all of these clock inputs are going to result in only one kind of output here. It's only, so you are basically going to get a trigger here. You are going to get a trigger here, or you are going to get a trigger here. This is the small amount of time when the flip-flop inputs is going to be toggled. Okay, and no longer toggle will be done because it doesn't matter how long it is on. This is for a narrow amount of time or a wide more amount of time. Next time when you get another trigger, the value will be toggled again. This is very important because now you can control the toggling in a more deterministic way. This could be used for implementing a lot of different circuits or state machines that uses JK flip-flops. Okay, so just to summarize, we have learned about the SR latch. After that, we saw how can we do a write enabled SR latch followed by a D latch, and we saw what were the disadvantages of a latch circuit and followed it up using a flip-flop circuit that is edge triggered. And we looked at two kinds of flip-flops. One was the D flip-flop, the other one is a JK flip-flop. Okay, so we will now look into the different kinds of designs that could be done using the D flip-flops or JK flip-flops, basically circuit design problems. And we are going to make various kinds of sequential logic circuit, for example registers or counters, which are an integral part of a computing system using these devices or using these circuits. So one thing that is new to us is the concept of excitation table, which is different than truth table. In truth table, what we have seen is a relationship in between the inputs and the outputs, right? So truth table is something that we have typically studied in case of a combinational circuit, and in a combinational circuit, a truth table tells you about the functional mapping. So if this is the input currently, what is the output that is going to happen? There is no notion of a temporal or time, right? So it doesn't matter what happened earlier in the circuit, what was the previous output to determine the current output. The current output purely depends on the current input in case of a combinational circuit. And in case of a sequential circuit, that is not the case. So we need to look into other strategies to analyze the behavior of the circuits. In case of a sequential circuit, we have a temporal dependency. For example, when we talked about the definitions of sequential circuit, we gave you an example of a counter circuit. And a counter circuit is going to count from some low value to high value if it is an up counter. So if it is a 3-bit counter circuit, it counts from 000, which is decimal 0, to 111, which is decimal 7, right? And you can see the count pens go from 0 to 1 to 2, 3, 4, 5, 6, 7, and from 7 it is again going to round up to 0, right? This is 7, then 0, then 1, 2, 3, 4, 5, 6, 7, then again 0, 1, 2, 3, 4, 5, 6, 7, and so on. So if you ask me that what is the state of the what is the next state of the counter circuit, I can't tell you an answer. I need to know what is the current state of the counter. Or if you ask me the current state of the counter without looking at the output, I have to tell me that what was the previous state of the counter. So if it was 4, definitely the next state is going to be 5. If the previous state was 6, definitely the next state is going to be 7, and so on. Okay. So what is important is that there is a temporal dependency, or if I know the current output, I can predict the next output for a given set of inputs. Okay. So you have to look at these are called excitation tables, and excitation table has these two things. One is the present state and the next state. Okay. So for any flip-flop or any sequential circuit that we are going to develop, these two columns are very important. One is your present state, okay, the set of present states, and the set of next states. Okay. So for a given bit, let's say the present state is 0, because one particular flip-flop could either be in a set state or reset state. So so if you recall that state diagram that I have drawn earlier, from the set state, it can either be in the next state could be the same thing set, or if it is in a set state, it can go to a reset state and vice versa, right? So if you see, if I have the state as 0, the next state is also 0. Okay. So two things could have happened. One thing is somebody applied j equal to 0 and k equal to 0. So this is originally q equal to 0. It happened to, so q next is also 0. This could be a memory hold state, right? Because j equal to 0, k equal to 0, I already know that's a memory hold state. Or somebody could have tried to set the value of q to 0. That is also acceptable. So somebody could have also given j equal to 0 and k is equal to 1, which also says that you are trying to reset the value of the circuit and q is going to be cleared off to 0. Okay, both of them are acceptable, where q equal to 0 and the next state is going to be 0 also. So in that case, that's why you are seeing this k as a don't care. So k could be either 0 or 1, doesn't matter. Okay. So in our truth table that you are going to draw, excitation table you are going to draw and simplify these values using k maps, this could be taken as a don't care condition. Okay. Similarly, the same thing is going to be reflected in this case, 1 and 1, right? So in case of 1 and 1, it could either be so let me show this 1 and 1 using this ink, right? This is 1, this is 1. So this could be either a memory hold, so j equal to 0 comma k equal to 0, or it could also be the case that you are trying to put the value of j is equal to 1, okay, and k is equal to 0. Okay, so this is also going to set the value of q to 1. So in that case, as you can see, j becomes the don't care, and here you can see this value of j is either 0 or 1, both are fine, but this has to be 0, k has to be 0, right? So this is your 1 to 1. Okay, similarly you can also figure out that if you want to go from 0 to 1, if you put j equal to 1, that should be enough, right? Because let's say q and qn, if it is 0 to 1, it could either mean toggle, which basically means j equal to 1, k equal to 1, or it could mean you want to put j equal to 1 for j equal to 1 for setting the value of q, right? So it is basically 1 0 or 1 1. It could either mean a toggle or you are either mean a set. Okay, so that's why it is 1 and don't care. So this is the reason you can just appreciate the truth table of the previous things that I have taught to understand this excitation table. And this excitation table is something that you need to be at your fingertips, right? So if I want to make a larger design that has multiple such flip-flops, and every flip-flop is going to change its state from 0 to 1 or 1 to 0, nothing is possible, nothing else is possible, or it is just going to retain the value. You need to kind of recall what value of j and k inputs is going to give rise to that particular scenario, okay, or we are going to achieve the transition, right? So primarily these transitions you need to remember very well: 0 to 0 or 1 to 1, and then 0 to 1 and 1 to 0. Okay, so 0 to 1 and 1 to 0 are primarily toggles, right? And or it's better to remember like this, because don't care sometimes help you to make the simplification much more easy, right? Because in K-maps, if you are for a like much larger circuit, if you have this x's, that is much easier for you to group terms, right? Of course, you can take both of them as toggles, right? If you put j equal to 1 and k equal to 1, this will absolutely be fine. Just that if you put let's say for if you just consider this don't cares, sometimes depending on if you want to go from 0 to 1 or 1 to 0, x is going to make sometimes your life easier. Okay, so this is what is meant by excitation table. So in the next class we'll try to build a simple circuit which is some pattern that is being generated by these LEDs. Okay, and we want to kind of create a circuit using these JK flip-flops that can give rise to this pattern.